Example, expected value number 1. Suppose you pay $3 to roll a fair die with the understanding that you will get back $5 for rolling a 3 or a 6, nothing otherwise. What is the expected value? Should you play the game or not? When we deal with a problem like this, the first thing we have to consider is we'll create a table something like this. The first column being the possible outcomes in words, then X net, so what is our net gain or loss, and then the third column is the probability of each of those possible outcomes. So immediately I hope it occurs to you that there are only two possible outcomes for playing this particular game, and that is you win or you lose. That's it. We're going to put it in words in that first column. What are the outcomes? Now, our second column needs to be numerical values that go with these. In this case, we're thinking about how much we gain or lose. So if you win this game, you don't walk away with $5. And make sure that's clear. You don't walk away with $5 because you're getting $5, but 3 of those dollars are yours that are returned, right? You already paid those. So really, you only have 2 new dollars. So X net here is going to be a positive 2. The second outcome here is losing. Well, losing, you actually don't gain any money, so you have lost 3, so you get negative 3. So winning has a numerical value of $2 to you, positive $2, and losing has a value of negative 3 to you. Next, we're going to think about our probability. The probability of winning here, in this game, there are 2 winning situations for you out of 6 because it's a fair die. So the probability is 2 out of 6 or 1 out of 3. Now, knowing that, the chance of losing this game is 4 out of 6, which is 2 out of 3. So you would expect in this game that a third of the time you would be gaining $2, and 2/3 of the time you'd be losing $3. So let's go ahead and find our expected value. For expected value, we'll take each of our X values, our numerical values, multiplied by their respective probabilities, and then we sum the result. So if I have 2 outcomes, I'm going to say first outcome times the first probability, second outcome times the second probability. But if there are 3, then I might actually repeat that process 3 times and find all the products and then add those up together. So my calculation for expected value, E of X, is 2 times 1/3 minus 3 times 2/3. And I'm using a minus instead of an addition there because I lost money in that case. So if I multiply 2 times 1/3 and then subtract 3 times 2/3, that gives me a result of, and I'm going to write this in decimal form, negative $1.33. So in the long run, if you played this game multiple times, an infinite number of times, on average, you would be losing $1.33. So, should we play this game or not? Well, the answer is a resounding no. You should expect to lose. You will win sometimes and you will lose sometimes, but on the whole, it is a losing proposition. Now, most games of chance like this have a negative expected value. The saying goes, the house always wins, okay? These games are designed for you to be losing money as you play, not for you to be winning money as you play. Just for fun, you should look up the expected value of playing the lottery. But that aside, there are lots of games like this, and they should have a negative expected value if the goal is for it to persist. Now there are games that are called fair games that have a net result or an expected value of 0. Like in the long run, You don't really expect to lose money. You don't really expect to gain money. They're just for fun. But this is definitely not what we would call a fair game. Example, expected value number 2. A 28-year-old man pays $97 for a 1-year life insurance policy with coverage of $100,000. If the probability that he will live through the year is 0.9992, what is the expected value for the insurance policy? In the case of something like this, the two outcomes in words would be that he lives through the year or that he dies during the year. Those are the two possible outcomes for an insurance policy. Now, let's assign numerical values to these. So if he lives through the year, then he doesn't use the insurance policy, which means he has lost $97 in the event that he has lived. He's paid $97 and has not gotten any return on that. Now, the numerical value for dying here is not, again, $100,000, because the insurance company will pay out $100,000 to whoever his beneficiary is, but $97 has already been paid. So let me just write this here. $100,000 minus $97 that he's already paid results in a total net gain of $99,903. Now, for the probabilities of these outcomes, we know that the probability he will live through the year is 0.9992. So that is our first probability, 0.9992. Now, the complement rule tells us to know the probability that of his death would be 1 minus 0.9992, which is 0.0008. Because these two values add to be 1. One of these two outcomes has to happen. Either he lives or he dies. No other options. So our expected value in this scenario would be E of x equals negative 97 times 0.9992 plus 99,903 times 0.0008. And the end result of that calculation would be negative $17. Now, in a circumstance like this, we don't ask, should you play this game? Because in that last example, losing $1.33 per game, okay, is completely a game of chance. So that is just a bad idea. In a case like this, the expected value can be negative and it still be a good idea. Because in this case, if on average you're losing $17 every year that you get a 1-year policy, if you have people who depend on you, if you have family, things like that, then, you know, I'd be willing to play the odds here that I'm going to lose money in the long run each time, but that because I might value their protection, things like that, it might still be worth doing this. But you have to give that some thought. Comparing the two, a game of chance versus something like a life insurance policy, very different things because there are very different stakes.